Today we're going to start our unit on equilibrium, and hopefully you've already seen the Edpuzzle, so you kind of have an idea of what equilibrium means. But I like to talk about evaporation and condensation. And so this is a phase change equilibrium. So let's assume that I have this cup of water in this closed system. So at the beginning, my water is going to evaporate. But since it's a closed system, everything's not going to evaporate. There's going to become a point where the air cannot hold any more water. And so some of these waters that have left will start condensing back in. And then the amount of humidity in the air will remain constant. That doesn't mean that we still don't have evaporation and condensation. It just means the rate of evaporation is going to equal the rate of condensation, so the percent humidity in this bell jar will remain constant. And here's what our reactions look like. We have H2O as a liquid and H2O as a gas. So some of these liquids are going to turn into gas, and some of the gas is going to turn into liquids. And so this is an equilibrium sign that shows that the reaction can go in the forward and the reverse direction. Right here, I have a chemical reaction. This is a phase change, but this is a chemical reaction. In ammonia in water is going to form the ammonium ion and the hydroxide ion. But then these two will react backwards and form back into ammonia and back into water. And when the rates are equal, it will have been said to be at equilibrium. This doesn't mean the concentrations are equal. It just means the concentrations are unchanging and the rates are equal. So as I've said, this equilibrium is dynamic. That means it's still reacting. So even though we don't see a change in amounts or concentrations, they are still going forwards and backwards, okay? So our equilibrium is when the rate of the forward and the reverse reactions are equal. Number one, the rates are equal. Number two, the concentrations are unchanging. And number three, the reaction is still happening. That's why it's a dynamic equilibrium. So I have two graphs here. One is concentration versus time. And equilibrium is achieved when the concentration of the reactants and the products are unchanging. Notice they're not equal here, but they've stopped changing. That doesn't mean that they've stopped reacting. The forward and the reverse reactions are just, the rate is equal, so our concentrations become unchanging. Okay, and if I look down here, we have the rate of the reaction, and when the rate of the forward and the reverse reaction is the same, that's when we're in equilibrium. So I have these two graphs lined up so you can see when my rate becomes the same, my concentrations will level off. So the rate of this forward reaction starts out really high and the rate of the reverse reaction starts out at 0. And that's because in this reaction, we started with all reactants. Okay, so our reactants are turning into products. In order for our products to turn into reactants, I have to make some products first, which is why our rate starts at 0. And then as I make more products, this rate increases, and as I use up the reactants, the forward reaction decreases until they become the same rate. So now we are going to, right here, this part you don't need, okay? But I'm going to show you where the equilibrium expression comes from. So here is our example, and these little a's, b's, and c's are your coefficients in your balanced equation. And right now, we have a rate forward, and remember our rate law is K times the concentration of the reactants, and then our rate reverse is K times the concentration of our product, because that is our reactants. And if I make them equal to each other, I can rearrange this equation, and it ends up being products over reactants will equal the forward over the reverse rate constant. And so what they do is they combine this into one number and they make it a capital K now instead of a tiny baby k. And that is our equilibrium constant, okay? Now, how do we write our equilibrium expression? It's K products concentration divided by reactants concentration, and they are raised to the coefficients because when we go backwards and forwards, these do equal out stoichiometrically. So now we can use our coefficients for those powers, and remember to get that from your balanced equation. Okay, so what's interesting here is because this all cancels out, we have no units for our equilibrium K, okay? And like rate, K is different at different temperatures. So let's practice writing. Okay, we do use coefficients in the expression. Here is an example with coefficients, and I want you to see the rate law versus the equilibrium expression. So if I'm going to write my rate law, it's rate equals K, concentration of A, B raised to some power. We need to figure that out elsewhere, okay? But now, when they're going forward and reverse, the stoichiometry does work out, and so our equilibrium expression is K equals products over reactants raised to their coefficients from the balanced equation. So remember, this is products, and these guys are reactants. And now I have a formula, and if I have the concentrations at equilibrium, I can plug them in and I can solve for my equilibrium constant. Okay? Gas pressures can be used instead of molarity, and it's the same thing. It's products over reactants raised to their power. And the other thing to know is we are going to be working with heterogeneous equilibrium. That means we have different phases. That means we have gases, solids, liquids. AQ means dissolved in water. The only thing that will go into your equilibrium expression are things that are in a gas phase or in our dissolved in water, our aqueous phase. Solids and liquids are not in the equilibrium constant expression. Why? Because they have unchanging concentrations. And if you want me to go more into that, meet with me after our lesson. Okay, so our equilibrium expression for this reaction, we don't do pure liquids and we don't do solids, so it would just be products. This is the only product that's aqueous, and we'll just put a little 1 there because that's my coefficient, divided by my reactants, and that's the only one that's aqueous. This is a solid and this is a liquid, so we don't put those in our equilibrium expression. Okay? So the last thing that we need to understand from this lesson is, what does K tell us? Remember, it's products over reactants. So if K is a very large number, greater than 1, let's start with if K equals 1. If K equals 1, my concentration over the products over reactants, those have to be the same because that's how I get 1, okay? But if I have more products, my numerator is a bigger number, and that means my K will be greater than 1. That means I have more products. And what do we say about that? We say that the equilibrium lies to the right. It's heavy on products, so the equilibrium lies more to the right. If K equals 1, they're equal, and my equilibrium is equal. And if I have more reactants, so I have a bigger number on the bottom, my K will be less than 1. And that means my equilibrium lies to the left because I have more reactants. So we say the equilibrium lies to the left.